Welcome back, everybody. So the first talk today is going to be by Claudia Fevola from the MPI Leipzig, and she's going to speak about nonlinear algebra and its Feynman.
Thank you for the introduction. Good morning, everybody. So I'll tell you about this ongoing project together with Daniele Agostini, Anna Laura Sattelberger, who's at the MPI, and Simon Telen, who's also in the audience. And so the goal is to talk about these type of integrals, which are in the literature called Euler integrals. And in particular, in part one, we'll be looking at the connection with what's called the twisted Rham cohomology. And this follows like a work that, in the context of Feynman integrals, was studied by Sebastian Mizera. And then in part two, we'll be looking at the connection of these integrals with the language of linear differential operators. And this follows instead some work by Beaton, Bogner, Clausen, and Panzer. Okay, and so finally, in part three, I'll try to tell you what's a Feynman integral. And how is this connected with Euler integrals, and everything we'll see in the first two parts. So let's first start by looking what's the Rham cohomology, and in particular, what's the twisted Rham cohomology, so that we're sure to be all on the same page. So to do this, we fix X to be a small variety. And some other notation we need is the space of regular k-forms over X. So this is a space of regular k-forms. And so the exterior derivatives together with the differentials give us a way to define a complex, which is the Rham complex. So the Rham complex is a sequence of maps which is defined in this way. So we have 0 forms, 1 forms, and so on. And we want that the images of each of these maps is contained in the kernel of the following one. And in particular, we can define cohomology. And to do this, I hope this is not too boring for some people, but we define what are called the closed form. So these are all k forms such that applying the differential gives us 0, and these are called closed k forms. And the exact forms instead are denoted with b, k, dr, and these are all the again k forms such that they can be written as the differential of some other form where now omega is a k minus 1 form. And these are what's called exact k forms. And since applying the differential twice give us 0, this tells us that the exact k-forms in particular are contained in the closed k-forms, and this is what gives us a way to define the kth, the Rham cohomology group. And we denote it by hk, dr of x, and this is just the quotient of closed forms modulo exact forms. All right, and then and then one can define, of course, the Euler characteristic, and the Euler characteristic of x is denoted by omega of x, and this is just the alternating sum of the dimension of these vector spaces. These are finite dimensional vector spaces, and one can consider the sum from 0 to n on minus 1 to the n times the dimension of each of these spaces. All right, but the tool we're going to use for connecting these with Euler integrals is actually a slightly different version of this complex, and it is what is called the twisted Rham complex. So we define the twisted Rham complex is the cohomology of this other complex that we denote by omega dot x with the new differential dh, where now dh is defined to be the classic differential plus a twist by a closed omega is a closed form. And in particular, what is nice about the twisted Rham complex is that there is an important theorem, which is also known as the vanishing theorem of the twisted Rham cohomology, that tells us that all the cohomology group, they just vanish, except for the top dimensional one. And this is just the notation for the cohomology group when looking at the twisted Rham complex. So what follows immediately from this, so one first fact is that if we define the twisted Euler characteristic, and we denote it by this as the sum of, so from 0 to n, again, the alternating sum in which now we consider these groups. So if we consider the dimensions of the hi x omega. Now, from the previous theorem, we just are left with the dimension of hn x omega. And an important fact is that this twisted Rham cohomology actually is the same as the classical Rham cohomology. So, this twisted Euler characteristic is the same as the Euler characteristic. So, when looking at the twisted Rham cohomology, in order to compute an Euler characteristic, we just need to know the dimension of such space. And And so the intuition that comes from physics is that when looking at, one can define some family of integrals coming from particle physics, and these integrals, they span a finite-dimensional family, and one is interested in computing the dimension of such space. So we want to find a basis of integrals in this family, and in the physics literature, these are called master integrals. So in order to connect these with what we will call Euler integrals, we need to introduce some notation. So we fix.
Can I ask a question?
Yeah.
I'm a little confused about the statement of the theorem. So first, omega has to be non-trivial, I suppose, because otherwise we get the
Yes.
And second, so is the statement that for every non-trivial form whatsoever, all cohomology vanishes, or that there exists one?
No, I believe it's for all. Oh my, yeah, yes, that's right. Okay, thank you for the question. So, okay, so we fix L polynomials F1, Fl to be polynomials in n variable with complex coefficients. So for us, this just denotes x will denote the vector of variables from 1 to n. And then we define x to be the complement of Cn minus the variety given by the product of these n polynomials times our n variables. So if you want, this is just C star n minus the variety of these L polynomials. And, okay, this is contained in the n-dimensional projective space, and we denote the border of x to be just the complement of Pn in Pn of this variety x. And okay, so now we can define the family of integrals in which we're interested in. So in the family of integrals defined in this way. So we denote I, A, B, the integral over gamma of x to the nu minus plus A minus 1 times f to the s plus b dx, where dx denotes just the n form, the x1 wedge, the xn, and here A and B are integer vectors, so these are just, they belong to z to the n plus l. Yes, so A corresponds to x and B to L, to F, and I need to tell you what's gamma. So gamma is a contour in Pn such that the border of gamma is contained in the border of x, and this is an n-dimensional integration contour. And also here I'm using multi-index notation, so when we write x to the epsilon f to the delta, we just denote x1 to the epsilon 1 times xn to the epsilon n times f1 to the delta 1 times fl to the delta l. And also 1 is just the n-dimensional vector with all entries of 1. So this is the family of integrals that we want to consider, where we are varying over all a and b.
Claudia, for clarity, what do you assume for mu and s? Are they?
Yes, and I was going to tell you this now. So mu and s are just fixed to be generic complex numbers. Yes. All right. Okay, so yes, let me write these. So we take mu and s to be generic complex numbers. So we let these be generic. And so the question we're interested in is what is the dimension of the C vector space obtained by considering C times the integrals we just defined. And let me stress that these integrals are taken to be a function of the contour. So we take A and B in Zn plus L. And so that's the question we're interested in, and the tools we want to use to compute this dimension is the twisted Rham cohomology. And okay, so let's first make some notation clear in order to understand what's the twisted Rham cohomology in this case. So the zeroth form over x are just given by linear combinations of the basis x to the a, f to the b. Instead, the kth form are given by elements of this type, so we sum over all possible indices, k indices, where we take hi1, ik, the x1 wedge, the i1, ik, and where hi1, ik is a zeroth form. Okay, and to define the twisted Rham cohomology, we need a non-trivial closed form, and we take minus omega to be the day log of x to the nu minus 1 times f to the s. And this will be an n minus 1 form. Okay, no, sorry, this is a 1 form. Okay. Okay, and this gives us a way to define, again, some twisted differentials. And in this case, the twisted differentials are just defined to be denoted by nabla I. And nabla I will go from omega I of x into omega I plus 1 of x. And this takes the ninth form and sends it into d minus omega wedge of phi. And okay, this is what defines our twisted Rham cohomology for the integrals. And okay, so in particular in this case, the cohomology modules hkx for this particular omega are given by just simply by definition, again, by the kernel of nabla k times the image of nabla k minus 1. And thanks to the theorems we saw before, we can conclude that the Euler characteristic of x is given by up to sine the dimension of h and x omega, so just the top dimensional one, and this is again just the dimension over c of omega k of x modeled out by the image of nabla k minus 1, because
K is n here?
that's right, yes. Okay, and this is telling us that we have a finite dimensional vector space, and if we then consider this family of integrals, we expect to have relations among these integrals. So the question now is like, how do we find these relations among the integral? Where do they come from? And okay, so to do that, we fix phi to be an n-1 form, and we take gamma inside p to the n such that the border gamma is contained in the 1 of x. And then by Stokes' theorem, one has the following equality. So we have that the integral over gamma of the x to the nu minus 1 f to the s phi. By Stokes' theorem, this is the same as the integral along the border gamma of x to the nu minus 1 f to the s of phi. And in particular, since for the way we defined x, we can conclude that the argument of the integral vanishes along the border, and this gives us the following equality. And okay, with some gymnastic, one can expand this integral, and this can be written as the integral over gamma of x to the nu minus 1 f to the s of nabla n minus 1 of phi. So how we can see explicitly, this is basically the relation among the integrals, and the way to see that is to write this more explicitly. So in particular here we can say that nabla n minus 1 of phi will be given by a linear combination over AB again to be, integer vectors of some coefficients A and B that will depend on the choice of phi times x to the A, f to the B, the x1 wedge, the xn. And we will see this more explicitly in a very easy example, and in particular, this gives the C-linear relation So we just need to plug this in this integral, and this will be equal to 0. And if we expand this, we will get something like this. So we have sum again over these integer vectors of these coefficients depending on phi times the integrals that we defined before. And these often in the physics literature are called IBP relation and are the relations that make this vector space finite dimensional. And
IBP is integration by parts.
yes, that's right. Yeah. All right. So what this is saying is that these IBP relations correspond to the image of these nabla n-1, and this gives us a way to identify these vector spaces. So did I give these a name? So if we call these vector space V, then we have that, okay, these are what are called IBP relations. And so this is telling us that V modulo these IBP relations is isomorphic to omega n of x modulo the image of nabla n-1, and this is just hn x omega. So this is saying that computing the dimension of the vector space V is the same as computing the Euler characteristic of x. And okay, so we can fastly see a very easy example. So the easiest case that we can consider is when we have one univariate polynomial. So the number polynomial and variable is 1, and so f belongs to phi of x. And the closed form that gives us the twist is minus omega, and this will be given by the d log. It's probably written there still, yes, of x nu minus 1 f to the s. And if one expands this is nu minus 1 over s over x dx plus s of f prime over f dx. And okay, so in order to generate relations, we need to consider an n-1 form, so a zero form in this case, and we need to plug it inside this integral. And so we take phi to be x to the a, f to the b, to belong to omega 0 of x, and we take a and b to be just integers in this case. So what we need to compute, as I said, is nabla 0 of phi. And in this case, this is given. This is just an easy computation in this case. And let me just write it. This is a plus nu minus 1 times x to the a minus 1 f to the s plus b plus s x to the a f prime f to the b minus 1 dx. All right, and so in order to get to see explicitly such a relation, we need, for example, to assume what is f. So if we take, for instance, f to be x plus 1, we can write our relation in this way. So the relation is already kind of visible from here. but we need to add the integral. So we plug these inside this expression, and what we get is the following. So we get a plus mu minus 1 times, now we have the integral coming from there, so we have I a minus 1b plus b plus s, and now here the first derivative is just 1, and so we have this term corresponding to a and b minus 1, and that's what we denoted by I a b minus 1. And so in this case, the Euler characteristic is just 1, and we would expect, and it's, one can show that from these relations at the end, one can just converge to the integral I0, 0. And so in the physics language, there would be just one master integral. All right. So now we want to pass to part 2. So understand this dimension of such vector space in the language of linear differential operators. So yeah, before that, maybe it's a good moment to stop in case there's any question.
Yeah, so you wrote E over there, and you wrote the curve gamma. Is there actually any dependence on the curve in the dimension calculation?
No, that's right. So these relations are independent from the contour of integration. Yes, good question. Okay.
I have a question. Is it possible to get any other relations besides integration by parts identities, or those will be the only ones they satisfy?
Those will be the only ones, yes.
Thanks.
Yeah, the ones following from Stokes' theorem, basically.
Thanks.
Small comment. There's a theorem by Deligne that says that the twisted Rham cohomology. I should start from the beginning. So one forms correspond to rank 1 local systems by duality, Serre duality, or let's say conjugation or Hodge theory.
Mm-hmm.
So to each one form, there's an associated local system, twisted local system. For instance, for the trivial one, for 0, it would be just C, so then we get the usual de Rham cohomology. But in general, Deligne's theorem is that twisted de Rham cohomology is isomorphic to the cohomology of the local system on X. So I'm not sure how that theorem can be true, that only Hn is non-zero. Maybe you're assuming something about X. Is it possible that you're making an assumption? There is a theorem about complements of hyperplane arrangements by, I don't know, Eno or Shechtman that says something like this. But in the general case, I'm not sure that twisted de Rham cohomology can always be true.
Okay.
Maybe.
I think my assumptions are just that X is a smooth algebraic variety, and
I think it should be true, at least in this case, where X is the complement of when X is a very affine variety.
it's a very fine variety. Yeah.
So
If
that's
you have
just
some special assumptions,
Right,
it makes
so at least
like
the-
the one
Yeah, on
we
X to
considered
be
here,
defined in that way.
like
yeah.
the one we consider here, I agree,
That's
but in general,
I see, I
don't
see.
think that it's possible.
I see. Okay.
It's just the cohomology of all rank 1 local systems that we
Okay. I see. Okay. Yeah. So X needs to be. In that case, it's true. Okay. Thank you for your comment. All right. So in order to switch gear, we need to introduce first some notation. So we denote by dn the n by algebra. So this is a free algebra which is generated by the element x1, xn, and the differential operators delta 1, delta n, and And this is a free algebra modulo, some relations, meaning that all variables commute, except that we have this relation, which is called commutator. So di and xi do not commute. So di xi minus xi di equals 1, and this is what it's called the nth algebra. And we denote by D, G, and M, where this denotes the multiplicative group of the torus, when we allow the x1, xn to be invertible. So this is again free algebra, and this can also be written in terms of what are called Euler operator. So here I can directly use the notation of the Euler operator, where theta I is xi the I, and finally the third algebra we need, the third algebra we need is what is called the shift-nth algebra, and this is denoted by Sn, and this is given by C with these symbols, so nu 1, nu n, sigma 1 plus minus 1, sigma n plus minus 1, where these are called the shift operators, and this is called the nth shift algebra. All right, and okay, so to connect these language of differential operators with integrals, there's an important transform which is called the Mellin transform. Of a function f from R to C, and this is defined in this way. So the Mellin transform of the function f is now a function in U, and it is defined to be the integral from 0 to infinity of x to the nu minus 1 f of x dx. And where one needs to assume that f decreases rapidly at 0 infinity to have the convergency of such integral. And some properties of the Mellin transform are given by the following relation. So one has that multiplication by x correspond to shifting the new variable by 1. So this is the Mellin transform of f of nu plus 1, and this is just visible straightforward from the integral. And the Mellin transform, so the action of the Euler operator gets transformed into multiplication by minus mu, so x times f prime, where f prime denotes the partial derivative with respect to x, is equal to minus mu times the Mellin transform of f of nu. And all right. And there's also a way to define algebraically And these definitions can all be extended to the multivariate case. So if we think about the integrals we saw before. Here by x, I'm really meaning just f in one variable. X is just a variable. I'm not taking multi-indexes. And so algebraically, one can define the Mellin transform is in this way. So this is an isomorphism of C algebras given by, so we denote this by brackets. So this is an isomorphism from this free algebra into the shift algebra. And the way this is defined is by sending xi into, so xi plus minus 1 into sigma I plus minus 1, and the other operator theta I is sent into minus mu I. And what this is telling us is that if one has an operator that annihilates a function, so if we have an operator here that when applied to this function give us 0, then this translates into some shift operators of the Mellin transform of that function. So yeah, what I just said is that if we take P such that applied to F, this gives us 0, then one has that the Mellin transform of P when applied to M to the F, and yeah, this is 0. So this gives us a way for passing from a relation in terms of F into a relation in terms of the integral, since the Mellin transform gives us the integral. And so one special relation is, for instance, the one given by the Bernstein-Sato polynomial. So we define the Bernstein-Sato polynomial B of F belonging to C with the variable of S of the polynomial F belonging to C, and in complete generality this is in Cn. This is the unique monic polynomial of lowest degree such that there exists an operator P of F inside D and extended with S, for which one has the following relation. So when applying P of F to F to the S, this is the same thing as multiplying the polynomial BF, let me write BF of S, to the function, sorry, this is S plus 1. This is the same as multiplying this polynomial times F to the S. And so here we just have so far relations between differential operators and a polynomial F. But we've seen that we can apply the Mellin transform to such relation in order to get a relation among integrals. So if we apply to this relation the Mellin transform, what we get is that the Mellin transform of P to the F applied to the Mellin transform of F to the S plus 1 is equal to B of F that stay invariant by the Mellin transform times the Mellin transform of f to the s. And now this Mellin transform, it's really the integrals in which we're interested in that depend on s and u. And so one of our goals is to understand what is the relation between the relations that one can obtain from the language of the Mellin transform and the relations that one can attain from the twisted Rham cohomology. And we expect for so the dimension, the vector space that one consider in this case is slightly different from the one defined before, because what's now varying is also s and u. So in this context, s and u are not fixed to be generic coefficients, but basically the new vector space is given by the sum again of a and b in z to the n plus l, and now we take not C vector space, but C as new vector spaces. And in particular, in this paper by Panzer et al., it was proven that the dimension of such vector space is also the Euler characteristic of the same very affine variety that we considered before. So we expect for these relations to match and to have a relation between these two contexts. And so yeah, that was pretty much all on this side. So before defining what's a Feynman integral, probably I can stop and ask whether there's any question. All right. Yeah, sure.
To clarify, so you said that the dimension of this is the same as the dimension of the previous vector space?
That's right.
Don't vary S and
Yes.
and here you're fixing the contour to be from 0 to infinity.
Yes.
And that because it doesn't depend.
Yeah, maybe ask. So what's the role of the Bernstein-Sato polynomial? It gives special relations, or why is this important, for instance?
It gives special relation. I don't really know special in what sense. For the Bernstein-Sato polynomial, for instance, we can match some relations. So for the univariate case, in every degree of a polynomial, we understand what's the operator that correspond to the relations coming, so to the n form that, to the n-1 form that we fixed in the Rham cohomology. But in general, these are just operators in the annihilating ideal of f to the s. Because if one consider p to the f times f to the s minus the Bernstein-Sato, this is, by definition, basically an operator in the annihilator idea. Yeah. All right. Thanks. Okay, so now I'll try my best to explain what's part 3 and what's a Feynman integral. And there are, I believe, many different definitions for these. I'll try to give the one which is more combinatorial. And one of my reference that I think is very understandable for mathematicians as well is the paper by Simon and Sebastian that Landau discriminant that Simon will tell about later. And okay, so to define a Feynman integral, we need to start from a Feynman diagram G, and we assume these to be connected and an undirected graph. And just to fix the notation, we denote by capital E the number of internal edges by n the number of external legs, and L is the number of independent loops. And in particular, we'll try to work this out. So we'll try to work out the Feynman integral associated to this graph, which is called the box diagram in the physics literature. So in this case, we're fixing E to B4 and also to B4, and we have one independent loop. And the idea is that these diagrams encode some interaction pattern about in a scattering process of the external particles, which are mediated by some internal particles. That's at least my understanding. And okay, so one needs to define the d-dimensional Minkowski space. So R1d minus 1 denotes the d-dimensional Minkowski momentum space. And the way one needs to think about points in this space, they're just vectors, real d-dimensional vectors, and this space comes with what is called the Minkowski pairing, which is defined in this way. So P times Q is given by the product of the first coordinates minus the product of all the others. So P2, Q2 minus P and Qn. And one needs to associate to the external x vectors Pi in R1 d minus 1, and these are called momentum vectors. And so these are associated to the external x. So we have P1, P2, P3, and P4. And to each internal edge, instead, we associate some complex parameters. So to each internal one, we associate an alpha E in C star, and these are called Schwinger parameters. So in this case, one has alpha 1, alpha 2, alpha 3, and alpha 4. And to each of these, one can also associate the masses, but these can also often be assumed to be 0. And in physics, usually the most studied case is the one in which d is equal to 4. And okay, so once we have these, we can define what's a Feynman integral, or at least one parameterization of these Feynman integrals. So a Feynman integral is an integral over the positive part of the e-dimensional real space And I'll write it and then tell you, try to explain what are these symbols. So we have d minus 2 times the exponential of I over h b of g d e alpha. Where, okay, so let me start from the end. D e alpha is just really the same notation we had so far. So this is d alpha 1 till d alpha e. I is just the square root of -1. H is what is called the Planck constant. This ng is a polynomial in the alpha, but the one thing that we want to mostly define is what is this b of g. So b of g is the quotient of two polynomials, fg and u of g, which are called the semantic, the first and the second semantic polynomials. And it is just the same u. And for defining these polynomials is where some combinatorics comes in. All right. So we denote by T of G the set of spanning trees of G. And then we can define the first semantic polynomial U of G to be the sum over all possible spanning trees of the graph of the product of all edges that I need to remove from such tree. So we have the product of the alpha e over all e that do not appear in the spanning tree. So for instance, for that graph, we can anytime remove one of the edge. So for that example, UG is given just by alpha 1 plus alpha 2 plus alpha 3 plus alpha 4. And to define the second semantic polynomials, we need some additional notation. So if we fix S to be a subset of the external legs of our tree, then we define Sorry, I need to define first what's a spanning 2T. So first we define a spanning 2T, and this is the union of two disjoint trees, T1 and T2, such that it contains all of the vertices of our tree, of our graph. So it contains all of in G. And then once we fix a subset S of the external legs, then we defined T of S. Let me write it in this way. So T of S will be the union of all possible spanning tree T of S, T of S bar such that T of S contains all the vertices attached to S, so all vertices to S, and no vertices attached to S bar, that this is just the complement of S with respect to the set of external legs. And okay, once we introduce this notation, we can now define the second semantic polynomial, F. Okay, yes, I promise. So FGS will be the sum over TS union TS bar in T of S of the product again of all the alpha E such that alpha gets removed by TS and TS bar. And finally, the second semantic polynomial FG is defined by the sum over all possible partitions of the n external legs. So these are disjoint non-empty set in P of G. And then one has the sum over all I in S of the vector Pi that we defined before, squared times the polynomials that we defined here, minus the sum from 1 to E of ME squared times the alpha E U G. And okay, maybe I'll stop, but okay, and it's an exercise to define these for that graph. And but this will be a sum of product of the alpha I, and it's a homogeneous polynomial in those alpha I. And the connection of just one last sentence is that the connection of these Feynman integrals with the Euler integrals that we defined before comes from the fact that there is another parameterization which is called the Lie-Pomeranski parameterization, in which one has that the F polynomial in the Euler type integrals will be just the sum of the two semantic polynomials. And so this provides a special example for the theory that we saw in the first two parts of the talk. And yeah, and I will stop here.